Hey guys, hello everyone and welcome to the channel. So here I am with the another part of this video in which we are taking 10 new questions, and we have already done two topics on this particular series. We have done coordination chemistry, we have done organometallic chemistry. In case if you have not watched that video, I'll give you link of that in the I button above. You can click there and watch those videos. So the series goes in this way that I upload questions 2 days prior to uploading the solution. You can see that questions from the website of ours. The link is there in the description. You can directly go over there and check out the questions and try to solve of your own. And after 2 days of uploading the question, I upload the solution, detailed solution on this channel. So in this way, it becomes a very good way of understanding the questions, of solving them, and to understand that what mistakes you are doing while doing the question of your own, right? So I hope this series is helping you out. If you want to give any feedback, you can give that in the comment sections below. I'll try to improve, or I'll try to make changes according to whatever suggestions you guys are going to give. Also, I would like to know which topic you guys want me to make next. This video will be about chemical thermodynamics. So now, without wasting any time, let's quickly jump into the video and let's have a detailed discussion of 10 questions on chemical thermodynamics. So let's take the first question here. It says what percentage Tc, that is temperature of the cold reservoir, is Th, that is temperature of the hot reservoir, for 20% efficiency of heat engine. It was pretty simple question, very straightforward. What you have to do is you have to use the formula of efficiency. So efficiency, that is given by eta, and that is equals to Th minus Tc divided by Th. Now in many cases you might have remembered it as like T2 minus T1 upon T2. That also doesn't matter, but this way Th and Tc makes it easier for you to understand what is the temperature of the hotter substance and what is the temperature of the colder substance. Okay, so that is just a way of remembering it. Now since the efficiency is given to you as 20%, so 20 means 20% means 20 upon 100, or you can even write it down as 0.2. And this, if you just separately divide it, so it becomes 1 minus Tc upon Th. Now if I try to solve it, so I can take this Tc upon Th to this side, so it becomes Tc upon Th, and this becomes 1 minus 20 upon 100. And if I solve this, LCM will be 100, 100 minus 20 will be 80. So basically I'll get Tc upon Th, and that will be 80 upon 100, or I can say it as 80%. So I can say that Tc is equals to 80% of Th, right? So pretty simple and straightforward solution. The correct answer comes out to be option number C, and that's how it has to be done. Very simple, just can be done in 2-3 steps. Now let's quickly jump to the next question of ours. Okay, here the question says that the given sample of water having mass m and temperature T1 is mixed with another sample of equal mass of water, but the temperature is T2. When T2 is greater than T1, if the process is done adiabatically and isobarically, then the total entropy change of the process is. Now here there are two things which you have to consider. First thing is that the sample of water has mass m only, but it has been kept at two different temperatures. So water only is kept at some temperature T1 and water only is kept at some temperature T2. You are mixing both the water and you are trying to find out that what will be the total entropy change. Okay, so that's what it is. So in order to go for that, first of all you need to find out that after mixing what is the actual temperature or what is the final temperature. Let's quickly understand it from example. Let's say you have a bucket of water. Okay, this is one of the bucket of water which is at some temperature T1, and you have one more bucket of water which is at some temperature T2. Now you are mixing both these waters to form a mixture of both of them, just like we do while bathing, while taking a bath during winters. So let's say I'm mixing both these water to get my next like final temperature. Let's call it as Tf. So basically this T1 will be the temperature which will also reach to some temperature Tf, and T2 will also reach to some temperature Tf. So Tf is the final temperature which the mixture reaches. So we need to find out first of all the value of Tf, and then we can apply it to solve and calculate it, the formula for the entropy. Okay, so we'll try to do it in that way. So let's first of all try to find out that what is the heat which is given to the system at some temperature T1. Okay, so now since both the steps are being done adiabatically and isobarically, So pressure is same and adiabatic process is there. So we'll try to apply the condition for adiabatic process. So in adiabatic process, QT1 will be equal to mCp, or yeah, so it will be mCp, and the final temperature, which is being Tf, which is the final temperature it is reaching, minus T1. That's the initial temperature from where you have started. Similarly, you are going to have QT2, that means the amount of heat which is exchanged for this. This will also be, because the mass of water is m in both the cases, so mCp, and this will be Tf and minus T2. Now, since the heat from one system is being transferred to the other, T2 is at higher temperature and T1 is at lower temperature. So while mixing, what will happen, that T2 is giving its heat to T1. So the heat exchange is taking place between the two species which are at temperature T1 and T2. So the heat, that is QT1, will be equal to minus QT2. Why is it so? Because the heat exchange is being taken place between both of them. So one will lose its heat and the other one is going to gain its heat. That's why the sign is different for both of them, and the amount of heat will be same for both of them. So we'll put the values from the relation which we have just developed. So mCp Tf minus T1, and this is going to equal to mCp Tf minus T2. Cancel out m and Cp, so you are going to get Tf, and here is a minus sign as well. So Tf minus T1, this is going to be equal to minus Tf and plus T2. On solving this, on taking Tf to the other side and T1 to the other side, you will get Tf is equals to T1 plus T2 divided by 2. So this is going to be my final temperature of the system. Now what I have to do is I have to find out my entropy of the change in entropy. Okay, so for that I will calculate my delta S. So delta S has a particular formula. Delta S is equals to mCp ln T2 by T1, or final by initial. So let's talk about this system which is at T1. So I'll write down here T1. So the system was initially at T1, but the final temperature is reached as Tf. So we will say mCp ln Tf by T1. That's the thing which you can do. And similarly for the other system, you will be able to do is at delta S T2, and that will be mCp ln Tf by T2, because here you are reaching to Tf from an initial temperature of T2. Now you can substitute the value of Tf which you have just calculated and try to solve it, because the total entropy is what you have to calculate. So let's try to calculate the total entropy, that is delta ST, or I will say total. This will be delta ST1 plus delta ST2. Take the sum of both of them, and what you are going to get is delta S total will be equal to, if you take the sum, m and Cp are going to be constant, so m and Cp will be constant, and in ln A plus ln B I'm going to apply directly, so it will be ln A into B, so it will become ln Tf square divided by T1 T2. Now this is what I got as my delta S total. I'm just using another slide to make the things clear to you. What you can do is you can write it down as this. You have ln as well, so you have mCp ln, and you can write down it as Tf upon T1 T2 under root and whole square of this, right? This is also you can write down, because on squaring you will get the same thing here. Now you can take this 2 outside. You can write it down as 2 mCp and ln Tf by T1 T2 under root, or you can put the value of Tf which you have all calculated as T1 plus T2 upon 2. So that will make it as 2 mCp, and it will be ln T1 plus T2 divided by 2 under root T1 T2. So this is going to be your total delta S. All right, and that should be your correct answer. So if you look upon here, your option number A becomes your correct choice for. All right, so this is how it has to be done. A little bit of calculation was needed, and it has to be understood that how heat transfer takes place from one body to the other body. All right, let's take the next question. All right, the next question is pretty simple. It says that the following TS plot shows the operation of two different cycles of an engine if T1, T2, S1, S2 are in the two plots as the same, then the cycle has the greater efficiency. So they are asking you that which cycle has greater efficiency. It is very simple to do. You need to know that efficiency in the TS diagram, okay, for TS diagram is basically area under the curve. Okay, so you just have to find out the area under the curve. So for this one, this whole area is going to give you the efficiency of this system, whereas for this this whole area will give you the efficiency of the system. Now how you will find out the area of this whole rectangle? It will be equal to length into width. So the length of this box is, or this whole thing is T1, okay, and the width is basically S1 minus S2. So this will be the area for this. Whereas if you have to calculate the area for this, you have to do it in the, like, either you can use the formula to calculate trapezium, the area of the trapezium, or you can calculate it as sum of the area of this triangle and this rectangle. But it is visually understood that this area is of course more, okay, this area is more than this one. This lacks from the previous one with this much value, with this dotted area. So this dotted area is smaller in the second case. So it was asked ki the cycle that has greater efficiency, so answer will be option number A. Diagram 1 has greater efficiency because it has more area. So whenever questions are asked on the basis of your diagram, TS diagram or PV diagram, try to solve them using diagram itself if it can be done. All right. Okay. So let's take the next question now. All right. So the next question here says that which of the following best describe the temperature and volume dependence of the state function U, G, and H for an ideal gas. Assume the temperature to be 300 Kelvin. Now they have given you different values over here and the best one which satisfies this. So you have to remember a few basic things, that you have two very important equations in thermodynamics. Those are called thermodynamic equation of state. Okay, thermodynamic equation of state. Now these thermodynamic equation of states are basically zero for ideal gas. According to the first thermodynamic equation of state, you have del U by del V at constant T, and this is equals to T del P by del T at constant V and minus P. That's what you have. Now you have to use your ideal gas equation to put the values here. So using ideal gas equation, which is PV is equals to RT or nRT, you can put it like that. So basically you want to find out value of P. So P is equals to RT upon V. Now if I have to differentiate pressure with respect to temperature, keeping my volume constant, so here R is already a constant, volume I have considered as constant. So R by V will come like that only, and temperature, differentiation of temperature with respect to temperature will be 1. So I'll only get R by V. I can substitute it over here. So let it be equation 1. So if I substitute it in 1, so I'll get du by dv at constant T. This is going to be equal to T is already here and its value is basically R by V minus P. Now this TR by V or RT by V is nothing but pressure. So you can put pressure here. So pressure minus pressure makes it 0, and that's why option number A becomes your correct choice. You can try it on the other options also, but others will not happen like that. So two thermodynamic equations are there. This is done through first thermodynamic equation of state. There is second thermodynamic equation of state as well, but that parameter is not given over here. I want you guys to tell me in the comment sections below that what you have on the left hand side of second thermodynamic equation of state. Okay, I just want to know that how many of you remember that which parameter do you have. Just like in the first thermodynamic equation of state, you have del U by del V at constant T. You guys have to tell me what do you have on the left hand side of second thermodynamic equation of state. All right. Okay, so let's take the next question then. Okay, here it says if U is the function of V and T, then del U by del T at constant pressure is equals to, okay. Now assume P and alpha is the pressure and the coefficient of thermal expansion, okay. So alpha is coefficient of thermal expansion, P is the pressure. They are asking you to find out the value of del U by del T at constant P. Alright, so let's try to answer it. It says ki U is function of V and T. So let's write it down like this. U is the function of V and T. Okay, U depends on both of them. So let me basically write it down in this way, that U is equals to function of V and T. Alright, now if some state function is dependent upon two different functions, so it can be written in this way, that du is equals to del U by del V at constant T dV and plus del U by del T at constant V dt. Okay, I want to know from you guys that what is this equation called, or like this representation, what do you call this type of representation? Okay, so now once you are done with this, also you know that from the first law of thermodynamics, let's call it as equation 1. So from first law of thermodynamics, what do you have? We have dq is equals to du plus pdv, right? That's what we have. Or you can say du is equals to dq minus pdv, so you can use that as well. So you will be having dq by dt. I'm just differentiating the whole equation with temperature. So dq by dt, and I'm putting pressure as constant. This will be equal to du by dt at constant p, and plus pressure is constant, so it will be dv by dt at constant p. Okay, that's what I'm going to get. Now you know that dq by dt at constant p is nothing but cp. Okay, it is cp. So cp is equals to this whole thing, that is del u or du by dt at constant p, and plus p dv by dt at constant p. Alright, so this is what I am going to get. Now it is already given key pressure you have to take as a small p. Okay, so this is pressure, you can put p, small p over there, and alpha is your thermal expansion, coefficient of thermal expansion. So what is the value of alpha? So we should know this, that alpha is equals to 1 upon v and dv by dt at constant p, or I can say ki dv by dt at constant p should be equal to alpha v, right? That's what we can do. So I'm just trying to do on this side. So basically I can write it down here, or dv by dt at constant p is equals to alpha v. Okay, let me call this equation as equation number 2, and this as equation number 3. Okay, so what I'm going to do, I'm going to substitute the value of dv by dt at constant p from equation 3 to equation 2. Okay, so from equation 3 and 2, what I'm going to get is cp is equals to del u by del t at constant p and plus p alpha v. That's what I will have, because p is already here, the value of this whole thing is alpha v, so p alpha v is what I'll get. What I need to know in the question is del u by del t at constant p. This is what I need to know. I'll take the other thing to the other side. So I'll have del u by del t at constant p. This is going to be equal to cp minus p alpha v, and this should be my final answer, which is there in option number D. So that's how it should be done. Ideally, this is just to show you, or just to explain you that this is how it can be written, but the solution starts from this, from the first law of thermodynamics, and that's how you can derive this. All right, I hope you have understood it well. The key for doing this question is to remember the formula for alpha, that is coefficient of thermal expansion. All right, let's take the next question then. All right, the next question is based upon entropy of mixing. It says if 2 moles of N2, 2 moles of H2 and 1 mole of CO2 are mixed, what will be the value of overall entropy of mixing at 400 Kelvin? Okay, so to do this, first thing is to find out, or let's write down the formula basically. So delta S of mixing is equals to minus R and sigma. There are various forms of this formula, just you can use any one of them. So it is minus R sigma Ni ln X. There is one more like R into N and Xi ln Xi. That also you can use, but this is what I'm going to use in this solution. Ni is the number of mole of that particular species, Xi is the mole fraction of that. So let's quickly calculate the mole fractions. So that is going to be like, if I calculate the mole fraction of N2, this is going to be equal to the number of moles of N2, that is 2, divided by total number of moles. Total moles is 2 plus 1, that is 5. So 2 upon 5 or 0.4, right? And if I have to calculate the number of moles of H2, so that will also follow the same thing, that will be 2 upon 5, because 2 moles of H2 is also used, that will also be 0.4. And if I have to calculate the number of moles of carbon dioxide, that is just 1 mole, so 1 by 5, and that will be 0.2. So I can now substitute everything here. So according to the formula, my delta S of mixing should be equal to minus and my value of R. Okay, so R, I'll leave this as it is, and then Here it will be like N1. So number of mole of nitrogen is 2 moles and ln 0.4 plus. Then comes hydrogen. So number of mole is 2, then ln 0.4, and then comes your plus for CO2. So number of mole is 1 and ln 0.2. Alright, so this is how you are going to have. Just substitute the value of R because you need the answer in joules per Kelvin. So R will be 8.314. And use your calculator to do this question further on, and that's how this you are going to get the answer. So on solving and on putting it, I'm not going to write it down. You can use your calculator to do it quickly. I have done it already, and my answer was coming as 43.84 joules per Kelvin. Okay, that makes option number C as the correct option for. This is how it has to be done. Let's go to the next question. Alright, it says that for a closed system, the pressure of the gas whose value of free energy A is minus beta Vt to the power 5 is identical with, okay. So for closed system, they have given key pressure of the gas whose free energy is like you have seen Gibbs free energy, and this one is Helmholtz free energy, that is minus beta Vt to the power 5, to which it is identical to, okay, where beta is some constant. So let's try to solve it quickly, that how we can approach it. So just for the context, I'll quickly tell that in the question it's given free energy of the system is minus beta Vt to the power 5, and what they are asking is pressure, okay, pressure of the gas is being asked. So let's quickly try to do. Now since A is already given to you, and we know that the value of your free energy depends according to the Maxwell equation, it is like dA is equals to minus S dt minus P dV. Okay, that's what you have. Now what you have to do is you have to convert this whole thing in the form of pressure. Okay, you have to like reduce this equation in the form of pressure. So I'm just going to differentiate the above equation with respect to volume at constant T. Okay, so at constant temperature, differentiating with respect to volume. So it will become dA by dV at constant T, and on this side, since temperature is constant, so dt will become 0 and this term will get vanished, right? And this part will be only, it will become minus P and dV by dV at constant T. So basically this will be 1. So I'm just erasing this for the sake of understanding. Okay, so dV ka differentiation will become 1 and this part will become 0. So you will only get minus P. Okay, so that's what you will get over here. All right, now, or we can say ki pressure is equals to minus dA by dV at constant T. So what does that mean? It means if I differentiate this equation with respect to volume keeping temperature as constant, so that will be dA by dV at constant T, and that should give me the value of pressure. So let it be equation number 1. So we'll do the same thing, differentiating equation 1 with respect to volume, okay, and at constant temperature. So if you are doing that, so that means ki dA by dV at constant T, it will become, beta is a constant, so it will remain as it is. T is being kept as constant, so Bt to the power 5 will remain as it is. Differentiation of V will obviously become dV by dV. So we can again erase that part because that will be equal to 1. So that means ki dA by dV at constant T is minus beta T to the power 5, or I can say ki minus dA by dV at constant T is equals to beta T to the power 5, and that is equals to the pressure according to this. So this is equation 3 and this is equation 2 and this is equation, let's say, 3. So from 2 and 3, what we can say? So from equation 2 and 3, we can clearly say ki pressure is equals to beta T to the power 5, and that should be our correct answer, option number A. All right, pretty simple. Just you need to understand that how you can approach. What was needed to do this? Maxwell relation. Okay, you can initiate it from the Maxwell relation itself. This has been taken from the Maxwell relation. All right, let's take the next question then. All right, let's try to do this question. Here it says that the value of del alpha by del P at constant T for the gaseous substance is identical with the following. Now you have different options in the form of beta. So you should know what is alpha and beta. Alpha has been already introduced to you in the previous question, that was coefficient of thermal expansion. Beta is compressibility factor. Okay. So now let's try to do this particular question. So what you have to start, or from where you have to start it, is that volume basically is function of temperature, this function of temperature and pressure. Okay, or you can basically write it down like volume is function of temperature and pressure both for the gaseous substance. So that means ki if you want to write down dV, that can be written as del V by del T at constant P dt plus del V by del P at constant T dP. This is how you can write it down. Again, we have used the similar concept of a state function which we have used in the previous question. Alright, so once you are done with this, let it be equation number 1. Okay. Now what I am going to do is I am just going to put the value of alpha. So since alpha is equals to 1 upon V and del V by del T at constant P, that's what it is. And del V by del T at constant P here also we have. So basically I can substitute the value here. What I'm going to do is I'm just going to write down that del V by del T at constant P is going to be alpha V. Let it be equation number 2. Okay, this is my equation number 2. Similarly, I also have equation for beta, and beta is equals to minus 1 upon V and del V by del P at constant T. So that will give me this factor. Or I can say ki del V by del P at constant T is equals to minus beta V. Okay, that's what I have. This is my equation number 3. Now, I can substitute the value of del V by del T at constant P from equation 2, and I can substitute the value of del V by del P at constant T from equation 3. So from equation 1, 2 and 3, what I am going to have is this ki dV is equals to, the value of this is alpha V, so it becomes alpha V dt plus, and the value of this is minus beta V, so basically it's minus beta V dP. Or I can simply divide the whole equation with V. So it will become dV by V is equals to alpha dt minus beta dP. That's how I'm going to get my equation. I can write it down properly. So yeah, that's what it is. Now this thing, this del V by dV by V can be written as d ln V. Okay, I'll explain you how this is. So it becomes alpha dt minus beta dP. Let me use the other slides. So what I just did is I wrote dV by V as I have written this whole thing as d ln V. It's pretty simple because you know ln x, differentiation of ln x, d by dx of ln x is equals to 1 by x, right? And if I don't have this dx part, let's say I only have d ln x, so this is going to be 1 by x and dx. If I just simply multiply this on the other side, right? So if I just want to show you, so I can take this dx from this division to this side, and it will become dx upon x. Similarly, dv upon v can be written as d ln v. So both the things are equivalent to each other. So what I got is d ln v is equals to alpha dt minus beta dp. So alpha dt minus beta dp. All right, fine. So that's what I got. Now, since we know, since volume is a state function, so it follows the Euler's reciprocal theorem. I'll explain you simply what Euler's reciprocal theorem says. Therefore, what you will say, since V is state function, therefore ln V is also a state function, because ln is just a thermodynamic function which is being operated, not thermodynamic function, it's a mathematical function which is operated on volume. So volume, if volume is a state function, so ln V should also be a state function. and that's why reciprocal or Euler's reciprocal theorem should be applicable on it. So what does it means? Simply, if you have seen any Euler's thermodynamic, Euler's reciprocal theorem, it goes like this. Let's say if you have df is equals to m dx plus n dy, so it should be dm by dy, okay, and at constant x should be equal to dn by dx at constant y. So you just have to take the cross. So m differentiating with the other one, keeping this as constant, should be equal to n differentiating with the other one and keeping this constant. So these things should be equal to each other. That's called Euler's. This is called, this thing which I just wrote is called Euler reciprocal theorem. Okay, so we can use the same thing over here, and considering the thing, what I can write down is the del alpha by del p should come at constant. The constant thing which will come here will be temperature, and this should be equal to del beta by del t, and the constant thing which will come here will be pressure. And since here we have minus sign, that's why I have to put minus also. So in the question, I guess it was asked to calculate del alpha by del p at constant t. So we have just calculated del alpha by del p at constant t, and this is equals to minus del beta by del t at constant p. So minus del beta by del t at constant p, and that's your option number C, and this should be your correct option, and this is how it has to be. All right, so it was pretty lengthy, but this is how it has to be done. Basic principle of Euler theorem and state function has been used to solve this question. All right, I hope this is much clear to you. Let's go to the next question. All right, let's try to do this question here. It says for solids and liquid, the value of del H by del P at constant T is close to. Okay. Now, this question can be done simply if you start doing from second thermodynamic equation of state. In that way also you will approach to the correct answer, or you can like try to do in a longer method. So any of the method you can use. If you are using second thermodynamic equation of state, things will become very easy for you. You can directly do it, but there one thing or one step will be there, that will be the value of del T by del P at constant del V by del T at constant pressure. So that term you will not be able to express that it is 0 or not, but I'll try to explain you how this will be done. So let's write down the value, the formula for dH. dH is equals to du plus you have or basically you can simply write it down as H. Enthalpy is equals to U plus PV. dH will be equal to du plus PdV plus VdP. Alright, that's how I can write it down. Now I can differentiate the whole equation with respect to pressure, so and taking T as constant, because that's what I need. So it will become dH by dP at constant T. This will become du by dP at constant T, plus here it will become P dV by dP at constant T, and plus since volume is there, dP by dP will become 1, so just V will remain. Okay, that's what you are going to get. Now this part is telling you change in internal energy with respect to change in pressure at some constant temperature. This factor is 0, and that's why you can just neglect this thing. We'll write down since du by dP at constant T is equals to 0. If you want, you can go one step, like one more step, you can add one more step, and you can write it down this thing. I'll just do it here in rough. You can write it down du by dP at constant T. You can write it down as du by dV at constant T, and multiplied by du by dV by dP at constant T. Now this tells you the change in internal energy with respect to change in volume at constant temperature. If the volume is changing, how the internal energy is changing for solids and liquids. So for any system, if the temperature is constant, there is no change in internal energy if the volume is changing. Okay, so that's why this factor will become 0, and that's why this whole thing will become 0. Simply you can write down that du by dP at constant T should be equal to 0 over here. So using that part, you will have dH by dP at constant T, that should be equal to P dV by dP at constant T and plus V. That's what you are going to have. Now here this part is telling you the variation of volume with change in pressure. So since solid and liquid are very less compressible, right? You cannot compress them. Thus, the variation in volume with changing pressure will not be much. So that's why dV by dP at some constant T will be roughly around 0. So this part will become 0, and that's what will be your final answer. That makes dH by dP at constant T is equals to V, and your option number C becomes correct choice for this. Alright. So 2-3 assumptions, or you can say 2-3 points which we are putting over here. One is that variation in volume with respect to pressure for solid and liquid is very less. You can consider it equal to 0. And the second thing is that we are also trying to put the variation in internal energy with respect to change in pressure at some constant temperature is equals to 0. Okay. So this is although not an assumption, but this is what you have taken as a near to 0 value. That's why it became. So option C is the correct option. Let's take the last question for this video. It says that the value of delta Hm, that is change in molar enthalpy of a gas undergoing isothermal expansion or compression is. Okay, so either expansion or compression, and the gas, obviously since you are getting A and B both, so the gas over here is a real gas. They are asking what is the value of delta Hm. So let's try to solve it quickly. Right, so to solve this question we will use the concept of Joule-Thomson coefficient. So that is given by mu Jt, that is our Joule-Thomson coefficient, and this is equals to 1 upon Cp and del H by del P at constant T, right? That's the one of the formula of Joule-Thomson coefficient in terms of enthalpy. Also we have one more formula of Joule-Thomson coefficient in terms of your real gas constant, or you can say in the terms of your inversion temperature and all. So that is given as 1 upon Cp, and you have 2A upon RT minus P, right? So that is also one of the equation which we have. Now you can relate these two things, these two equations, and you will be able to find out what you need. Okay, so let's try to do it. So Cp and Cp will get cancelled out. You will get minus dH by dP at constant T is equals to 2A upon RT minus B. Simply multiply with minus sign and take RT as the LCM. So you will have dH by dP at constant T is equals to this is going to become BRT minus 2A and divided by RT. How it became? Because I have multiplied with minus, so this became minus and this became plus. So that's how it is. And I have also taken RT as the LCM. So BRT, that's how. Now you don't need dH by dP at constant T. So you can simply remove this temperature here, and you can write it down in the place of dH as delta H, and in the place of dP you can write it down as delta P, and on the other side it will be like BRT minus 2A and divided by RT is as such. So your delta H becomes BRT minus 2A divided by RT and whole of this thing multiplied by delta V. This has to be delta P, right? So delta P should be here, right? Now it is correct because I just wrote delta V in place of delta. Fine. So it should be delta Hm is equals to BRT minus 2A upon RT delta P, and your option A is actually correct, not D. Okay, option A should be correct. So that was a quick mistake which I just like tried to fix it out. So that's it. That's how these questions need to be done, and that's how these 10 questions are done for this particular video. I hope you guys understood. I hope you guys liked the video and you understood the concept behind each and every question, and do let me know which topic you guys want to be discussed in the next video. So that's it for this video, guys. Thank you so much for watching this, and I will see you guys in the next one. Till then, have a great day. Bye bye. Hey guys, so I teach live on Unacademy Plus platform. Here I teach for the CSIR UGC NET category, and you can follow me over here for regular classes. You can access my free classes as well as my paid classes on this particular platform. The classes which are free, you can get that under the section of special classes, whereas in order to access my paid classes, paid live classes, you have to take Unacademy Plus subscription. So do make sure that you take the Unacademy Plus subscription to access all my paid classes, which are quite organized. The whole syllabus is being completed over there and the classes are quite regular over there. So make sure that you take Unacademy Plus subscription by using my referral code, that is N_Huda. That's it for this. Thank you so much.